Hello all. So in the last session we were discussing about the best practices in developing NLP applications. So we have covered the concept of batching instances. So we have seen three basic methods of performing batching instances, that is by padding, sorting and masking. So today in this session I would like to discuss about another concept or another best practice in developing NLP application, which is tokenization for neural models. So in the last class we have seen few techniques to we use to build a model, right? So batching instances is done. So today we will see how to handle unknown words, that is tokenization for neural models. Because when we talk about NLP application, the input that we give would be a sequence or a sentence, and the model will not understand this particular sequence or sentence, for which the first and foremost step that we do is tokenization. So how do we tokenize the neural models, that is character models or subword models, is what we will discuss today in the session. Okay, so basically in the previous chapters we have covered the basic linguistic units, right? So we have seen we start with words, or we start with characters, words, and then engrams, right? So we have also seen how do we compute their word embeddings, right? So in this session I would like to go deeper and focus on how do we analyze text and obtain these units with the process called tokenization. Okay, so neural network models pose a set of unique challenges with the way they deal with tokens. Okay, so we'll cover some of the modern models to deal with these challenges. Okay, so when I talk about these challenges, we have two things that we consider, which are called as unknown words. We consider character models and subword models. Okay, now when I talk about these unknown words, okay, so basically when we talk about vocabulary, okay, so we talk about vocabulary, right? So when I talk about vocabulary, it is a set of tokens that an NLP model will deal with, right? So many neural NLP models operate with a fixed or finite set of tokens. For example, when we have built a sentiment analysis, okay, so we first tokenize the training data set and then structure the vocabulary object that consists of all unique tokens, and then uh, you know uh, we then using an embedding layer to convert these tokens into word embeddings, which are some abstract representation of the input tokens. So far it was good, right? But the number of all words in the world is not finite, right? So we won't deal with finite set of words, right? We constantly make up new words that didn't exist before, right? So when we talk about NLP, the words which were used in developing the word vocabulary earlier was different, and the new words, so many new words have come into existence now. Now, what if the model receives a word that it has never seen during training? That is the most important or major problem, right? So, because the word is not part of the vocabulary, the model cannot even convert it into an index, or let alone look up to its embeddings. So such words are called as OOV words, or out of vocabulary words. Okay, and they are one of the biggest problem, or one of the most important challenge that we actually come across when we try to build NLP application. By far, the most common way to deal with this problem is to represent all these OOV tokens as a special token. Okay, so we represent all these OOV token as what? Special tokens. Okay, now when I talk about special tokens, it is conventionally named UNK, unknown words. Okay, now the idea is that every time the model sees a token that is not part of the vocabulary, it pretends it saw a special token called UNK, unknown word, instead and it will proceed as usual. Okay, this means that the vocabulary and the embedding table, we have vocabulary table, embedding table, both have a designated slots for these UNK words, so that the model can deal with words that it has never seen. Okay, now do you see any problems with this approach, treating all OOV tokens with a single UNK token means that they are all collapsed into a single embedding vector. Okay, it doesn't matter if the word is NLP or if the word is doggy. If they are not available in the vocabulary, they are represented as unknown token. As long as it's something unseen, it always gets treated as UNK token and assigned with the same vector. Now this becomes generic. Will catch all representation of unit word. Because of this, the model cannot tell the differences among OOV words. When I talk about two different words called NLP and OOV, both of them are given the same vector. So both of them means the same. Okay, so this may be fine if you are building, for example, a sentiment analyzer. OOV words are by definition very rare and might not affect the prediction of most of the input sentences. However, this becomes a huge problem if you are building a machine translation system. For sentiment analysis, it does not have much effect, right? But when you talk about uh, other applications like machine translation, this would be a major problem. Okay, or conversational engine like chatbots also, it wouldn't be usable empty system or a chatbot if it produces, I don't know, every time it sees the new words, right? Every time it sees the new words, I can't say I don't know. In general, this particular OOV problem is more serious for language generation applications like machine translation or chatbots like conversational AI compared to other NLP systems for prediction like POS tagging or sentiment analysis. So how can we do better? How can we do better? OOV tokens are such a big problem in NLP that there has been a lot of research work on how to deal with this problem. Okay, so we will see how do we overcome this particular problem by using these two techniques, that is character models and subword models. Okay, so these two techniques basically are used for building uh, character models and subword models. Okay, so these two techniques are commonly used for building robust neural NLP models which solves this problem of unknown words or out of vocabulary words in the process of tokenization. Okay, so let's talk about character models. Okay, so when I talk about character models, the simplest yet effective solution for dealing with OOV problem is to treat character as tokens. Okay, so we break the input text into individual characters. Even including punctuation and white space are also considered as regular tokens. Okay, now the rest of the application, we have no change. The rest of the application is same, but the only thing that we change here is treating characters as tokens instead of words. Okay, now the word embeddings are assigned to characters which are further processed by the model. If the model produces text, it does by character, not the word by word. The model produces text character by character. In fact, we already use this character level models, right? So we built a language generator using character models where we take token by token, character by token, that is letters individually for generating text word by word. So we have used RNN model which produces text character by character, and then which also includes white space. Okay, so as you can see here in this particular figure, thanks to this strategy, the model was able to produce words that look like English but actually aren't. Notice a number of peculiar words. For example, when we talk about words like deposit, or when we talk about studented, okay, distaples, that resemble English words in the output. Okay, if the model is operated on such kind of words, it produces only known words like uh, despite, studented, distaples. If you use such kind of different words, they give us UNK tokens, and this wouldn't be possible. Okay, now how do we actually solve this problem? Okay, so these character based models are versatile and put few assumptions on the structure of the language. Okay, so when I talk about structure of the language, For languages with small set of alphabets like English, okay, it effectively eradicates unknown words because almost any words, no matter how rare they are, can be broken down into characters. Okay, tokenizing into characters is also an effective strategy for languages with alphabets like Chinese, Japanese, although you need to watch out for unknown character problems. Okay, however, this strategy this also has problems. Character based words also has problems. Okay, the biggest issue is its inefficiency. Okay, for example, to encode a sentence, the network needs to go through all the characters in it. For example, when you talk about character-based models, it needs to process the as THE, including the white space, that is dot. Okay, to process a single word the, it is taking white space also into consideration, whereas a word-based model can finish this in a single step. So this efficiency takes its biggest toll on the transformers, where the attention computation requires quadratically uh, increases quadratically when the input sequences gets longer and longer. Okay, so hence we don't usually use character based model, but we go for the second model, which is called as subword models. Okay, now so far we have studied two extremes: the word based approach, which is efficient but not great at dealing with unknown words, and then we have seen the character based approach, which is great at dealing with unknown words but it is efficient. Okay, so is there something in between word and character? Yes, we now use the next concept, which is called as subword models. Okay, subword models are the recent innovations that addresses this problem for neural network models. Okay, so what we basically do here is, in subword models, the input text is segmented into units called subwords. Let me repeat: the input text is segmented into unit called subwords, which simply means something smaller than words. Okay, larger than characters, smaller than words. There is no formal linguistic definition as to what subwords actually are. I can't tell you exactly what subwords actually are. So they are in between the characters and the words. Okay, but they are roughly correspond to some part of the word that appear frequently. For example, one way to segment, suppose let me take dishwasher. Okay, so one way to segment is dish plus wash plus air. Although some other segmentation is also possible, you can use varieties of algorithms such as word peas or sentence peas, tokenize words into subwords. Okay, but by far the most widely used method for generating subword tokens is BPE, which stands for byte pair encoding. I repeat, for generating, we are done with word based, we are done with character based. So the final proper way to solve this tokenization is using subword models, and there are different ways in which you can subword the given word. So one such method is called as BPE, which stands for byte pair encoding. Okay, now this BPE was originally invented as a comprehension algorithm, but since 2016 it has been widely used as a tokenization method for our neural network models, particularly when we talk about machine translation, where I can't go with word tokening or character tokening. Okay, now when we talk about this BPE, byte pair encoding, the basic concept for neural or BPE is to refer frequent words such as the, you, basically engrams. Okay, such as able, anti, which are unsegmented, while breaking up rarer words such as dishwasher into subwords like dish plus wash plus okay, keeping frequent words and engrams together. Please understand, we are concentrating on frequent words and engrams together. This will help the model process these tokens effectively, whereas breaking up rare words ensures that there are no UNK tokens or unknown tokens, because everything can be ultimately broken up into individual characters if necessary by flexibly choosing where to token based on the frequency. Okay, so in this way BPE achieves the best of the two models, being efficient while addressing unknown word token problems. Okay, now let's see how BPE determines where to tokenize the real life examples. Okay, so as I told you earlier, BPE is basically a statistical algorithm. It doesn't use any language dependent information. It operates simply by merging the most frequently occurring pair of consecutive tokens one at a time. Okay, so what BP first does is BP tokenizes all the input text into individual characters. For example, if your input word is 4 words, okay, low, lowest, newer, and wider. Okay, it will first tokenize them into low underscore, lowest, newer, and wider. Here we are using this underscore word because I'm using this underscore token here because it is a special symbol that indicates the end of each word. Okay, so I'm taking low, lowest, newer, wider. For each and every sentence I'm using underword which is end of the word. Okay, then the algorithm identifies any two consecutive elements that appear most often. So here in this case LO, here in this case LOW. Okay, so LO appears most first 2 times so that these characters are merged. Okay, so offering LOW as the new sub word. Okay? So in this way we will uh, make BPE learn subword units by iteratively merging consecutive units that co-occur frequently. Okay, so notice that in this particular thing, after 4 merge operations, the lowest is segmented into LOW, LOWEST, where frequent substrings such as low are merged together, whereas infrequent words such as EST are broken apart. Okay, so to segment a new input, example lower, the same sequence of merge operations is applied in order, yielding low into one thing, ER into another thing. Okay, so if you start from 52 unique letters, 26 uppercase and lowercase, you'll end up with 52 plus n unique tokens in your vocabulary. Okay, where n stands for the number of merge operations which are executed. So in this way, you have complete control over the size of the vocabulary. Okay, so this is how we use tokenization. We don't go for character tokenization, we don't go for word tokenization, but we use BPE. Okay, byte pair encoding subword models to avoid the problem of tokenization in generating real-time NLP models. Thank you.